last time we introduced the chapter 14, so it's about spontaneous change. And basically in this chapter we will learn this entropy, and also we will introduce the free energy. Okay. So the first part is about entropy, and then we introduced the change, spontaneous change. So spontaneous change is one that occurs without external intervention and has a definite direction. So like the ice can change it. When the temperature is more than 0 degrees, so the ice can change it to water. And when the temperature is more than 0 degrees, so it will change it to ice. Okay. So basically, for a reaction, if it release heat, so this means the system will lose energy. So basically, this kind of reaction is spontaneous. But sometimes the reactions absorb energy from environment. They also may be spontaneous. Why? Because there are two facts to determine the spontaneity. One is energy. If the reaction releases energy, of course, it's good for this reaction. And the second factor is matter tend to become more disordered. And this disordered is entropy. So this is what about entropy. So for those reactions absorbing energy from environment, they tend to, the after reaction, all matters tend to become more disordered. So these reactions can also be spontaneous. Okay. So how to determine the entropy? Is about the disorder, and then we introduce, for example, for this process, when it's closed, it's like just a B as gas. A is empty, is vacuum. When it opens the wave, you can see the gas can go from B to A, and this from this state to this state, it's spontaneous. But when the here is open, it will not tend to back, right? So this from this state to this state is not spontaneous. We also introduced the states. If only two gas molecules, only two, one is like red, it's blue. So when it's closed, it's only one state, right? Only one state. It's supposed to. But when we open here, it can have four states. All four states are possible. So when it's open, so the arrangement of B is more than A. Here is only one, but four. The arrangement number is 4. So this B state is more disordered. Okay. And so from A to B is spontaneous, but from B to A is not spontaneous. Because basically, we know for the process, it should tend to become more disordered. So from A to B become more disordered, but from B to A it becomes less disordered. So So from A to B is spontaneous. From B to A is not. Is spontaneous. And if we think about more molecules, like four molecules, okay, and there are more elements, and from A, this state to B is spontaneous. For example, ice. The ice melts is spontaneity when temperature is more than 0 degree. So it is an endothermic process. So we know for ice can become water. It need energy from environment, but this process is still spontaneous. The reason is when the ice changes to water, the disorder increase or decrease? Yeah, increase. Yeah, disorder increase. For example, when it is solid, and all the molecules are fixed in their positions. They cannot move, right? But when the ice change to water, so they can move. So they can move. This means they become more disordered. So ice change to water, the disorder increase. So this process is also spontaneous. Because melting increases the disorder of the system. Okay. So here, the entropy. So entropy of a system quantity, the degree of disorder or randomness in the system. So it's the larger the number of arrangements available to the system, larger is the entropy of the system. Okay. So this means the system has more arrangements. It has higher, more entropy. So an entropy is a state function. The change in entropy during a process, delta S, depends on the initial and final entropies of the system. So the entropy change can be used this equation. Okay. Delta S equal final minus the initial. And if delta S is more than 0, this means the final entropy is larger than the initial. Okay. So this is what we introduced last time. So it's about what is entropy. So basically, entropy is the disorder of the system. And for spontaneous process, its entropy should increase, basically increase. Okay, now we introduce the third law of thermodynamics. So since entropy is related to the number of possible states a system can occur, all states being equal in energy. All states being equal in energy means they have the same possibility to occur. Okay. So we can determine the absolute value of entropy. So how to determine the value of entropy? So we're using this equation. Okay. So this entropy S equal K. K is a constant. It's called Boltzmann constant. And the number is this number. Okay. This is the K number. And ln, right? And W. W is the number of ways or like microstates that the atoms or molecules of a sample can be arranged. So each microstate be equal in energy. So here we can use this equation to calculate the entropy of the substance. And the K is a constant. And this is the arrangement. You can give an example. For example, in this case, if we just consider we consider only 4 molecules, okay, and we know when the 4 molecules, carbon oxide molecules, at 0 K, what's 0 K? 0 K is the lowest temperature we can arrive, right? So it's minus 253, okay? So this is also absolutely zero, absolutely low temperature. We can write. So when the temperature is 0 K, what does this mean? This means they can't move, they can't rotate, right? They can't vibrate. So they're only one state, right? They can just freeze, like freeze. They are freeze. Okay, they are freeze. Only this state. So in this here, so the arrangement is only one, right? Only one. We know if the arrangement is only one, so the this number will be 0, right? 0. So the S number, and entropy is 0, and the unit is J is Joule and Kelvin, okay, temperature. So this means for all substance, when the temperature is at 0 K, so this means the molecules or atoms in the substance are freezed. So there are only one arrangement. So in this case, their entropy is 0. Their entropy are 0. Entropies are 0. Their entropies are 0. So this is third law of thermodynamics. Third law of dynamics. So this the entropy of a like crystalline substance at the equilibrium approaches 0. This is 0 as the absolute 0 of temperature. Absolute 0 of temperature is 0 K. Okay, 0 K is also called absolute 0 of temperature. If 0 degree is not absolutely, so the unit is K. Okay, can you get the temperature like -1 K? -1 K? No. Okay, -1 degree is okay, right? But -1 can know. The lowest temperature is only 0 K. Okay, this temperature is 0 K. So at this temperature, so you know the temperature is not like volume. Volume you can as large as possible, right? For example, the space, the universe, you don't know the volume of the space, right? And you also don't know the mass of the universe, right? Of the space. But we know the lowest temperature. The lowest temperature in the universe is only 0 K. Okay. So when the substance at 0 K is entropy is 0. Okay. So this is the third law of thermodynamics. And this why 0 is from this equation. Because the arrangement is only 1. If K is 1, so this number is 0. So the entropy is 0. Okay. So this is about the third law of thermodynamics. So any question for this? Okay. Okay, but we know Of course, if the temperature is more than 1K, so for example, for these four molecules, right? So they can root, right? So for example, they can like have this 16 ways of arrangement for four carbon oxide molecules, right? In this case, for example, the red one all at the right? But in this case, this guy, the red one, red is oxygen, okay? The oxygen is at the left, right? In this case, this guy's oxygen is at the left. Okay, they can make, because they can rotate, so they may show more arrangements. And because this guy, okay, so this guy, all oxygen atoms are at the right, but in this case, all oxygen atoms are at the left, right? So between these two states, there are more like these arrangements. So we can calculate what the entropy of this state of the like four molecules. Their arrangement what the entropy. So we can say like, so we can still using this equation, right? So here W is 16, right? 16, okay, 16 times this, and the constant. So for this arrangement, just only this arrangement, the entropy is this number. And of course, if four molecules, only this kind of arrangements? No, because for example, the red one can also at the top, right? Can also at the top, right? The red oxygen can also at the 10 to down, right? So this means this is just only one very simple example to show how to calculate the entropy. But of course, for formula effect, for four molecules, there are much more arrangements. It's not only this 16, right? 16. Okay, so this is one. The molecules can translate, can vibrate, and can rotate. So this means each of these motions contribute to the molecular's degree of freedom. So molecules have three, like it. For example, for translate degree, they have translate more than one. Okay, they have like three translation degrees of freedom. They have 2 or 3 rational degrees. For example, 3 degree, like x-axis, y-axis, and the z-axis. Okay. And also the vibration degree, vibration of freedom. Vibration means like, for example, this for carbon and oxygen, the vibrate can like this. For example, if this carbon, this oxygen, they can like this vibrate. Okay, so can like this vibrate. Those vibrate, right? So they have more number of degrees of freedom. And the larger the degrees of freedom that the system can expect, higher is the entropy of the system. Because if the degree of freedom is larger, so this means they are more free. They have more freedom. If they have more freedom, this means they can have more disordered. So more disordered means they have higher entropy. Okay. So basically, for example, So using this way, we can compare the entropy of two molecules. For example, hydrogen. Okay. So basically, hydrogen has fewer vibration degree of freedom than carbon and hydrochloride. Why? Question. Why we can see this guy has more vibration than this guy? Yeah. Why? Why this guy has more like freedom than this guy?
I think it's because hydrogen is a gas and calcium.
Oh no, this also can be gas. This also can be gas. Okay.
Or maybe there's the spaces in between the molecules of hydrogen are loosely packed, so the vibration like this and on calcium chloride, so the degree of freedom is yes.
Okay. So basically here we can say for hydrogen, how many atoms? Two. This guy. Five, right?
Yes.
So for example, vibration. So hydrogen to only two, right? Why hydrogen to hydrogen? They only like this way, right? Or this way, right? The three freedoms, right? But for carbon, 1, 2, 3, 4. So they can like this chloride can like this and this. Okay, this can like this and this chloride can like this. So there are many freedoms. Yeah, they have more possible for vibrating that because it has more atoms. So the entropy of hydrogen is less than that of CCl4. Okay. So basically, if the molecule has more atoms, so it has higher entropy. It is higher because it has more arrangements for their atoms. And also for the same molecule, the gas, the entropy of gas is larger than that of liquid or that of solid. Okay, I remember last time we did. And of course, the solid, all the atoms can move, right? Can move. But the liquid can move. And of course, gas has more arrangements. So this table, this table we can see the entropy of the substance, and this entropy can be measured from experiments, from some measure or calculate. Okay, calculate. And for example, if you want to know how to calculate or how to measure, you don't have time to introduce this here. Okay, for example, for the gaseous water. Okay, its entropy is 188.8 joule. The unit is joule, mole, and okay. But the liquid is only 69.9. So you can see the vapor of water has larger entropy than the liquid water. Right? Okay. And here to show. And you can find the entropy of all substance from book. Yeah, if you look at the book. I remember you get one. You have a book. Someone show me the copy of the book. You know, if you have the book, you can find this data from book. Okay. This step just show this substance. Okay. So here introduce the expression for change in entropy. So here there are two pictures. So like this is system, okay. This is surrounding, okay. And in these two pictures, the system, both systems get heat from the environment, from it. But what the difference? The difference is, in this case, the temperature is warm. This is cool. So this means this temperature is higher than this temperature. That's this temperature. The system, this temperature is higher than this temperature. And but the heat, the amount of heat is same for both cases. This is the entropy change. So in this case, the entropy change is lower than this case. What this mean? So this means when the substance at high temperature, its entropy change is small than that with low temperature. Even though they get the same heat. So basically, if the substance get heat, so this means its temperature will increase, right? If the substance get heat, its entropy will increase or decrease. If a substance get heat from environment, its entropy will increase or decrease. Yeah, basically increase. Because when it has high temperature, so it's like move fast, right? So it's more disordered. So all substance, if they are temperature increase, they are disordered, will increase. And of course, if there are temperature decrease, their entropies will also decrease. This is like water, right? The entropy of water is higher than that of ice, right? The water has high temperature than ice, right? And of the gas, the vapor of water has a higher entropy than water, the liquid water. That's the question.
Actually, earlier you said when, I don't know if you said, okay, when the substance is melting, the entropy increases.
Yes.
And also when it's boiling, it also increases.
What?
Also, like when it's boiling, it also increases.
Yeah, it's boiling also increases. It changes to gas, also increase. Because for example, the ice, all the atoms in the ice, they just fix, right? They can't move. Yeah. But in the liquid, when they change to water, liquid water, they can move. So they are more free, right? And if it's changed, but in the water, they can just move in the water space, right? But when become vapor, they can move, they have more space to move, right? So they are more freedom, so they have more entropy. So when the boil, the water changes to gas, the gas has higher temperature and also has more entropy. It's more entropy because they have more space to move, right? Okay. So here this means a process accompanied by a large amount of heat correlates to a large degree of disorder. And so that exchange of entropy is proportional to heat. And of course, if the substance gets more energy, it will has higher temperature, and it will go much faster, and it is more. This means it is more freedom, right? It's more freedom. So when the substance gets more heat, its entropy will also increase. So the entropy change is proportional to heat. Okay, so this is no problem, right? Okay, and the great change in disorder occurs if the temperature at which process is carried out is low than when it is high. So this is like in this case. So when the temperature is low, the change of the entropy will be high. The same heat, okay? The same substance, when they get the same heat, but at a different degree, When at a low degree, the entropy change is larger than that at high temperature. So you can say this is the change of entropy. In this case, is higher than this. Okay. So this means the entropy change is proportional to the reciprocal of the temperature. Okay, it's like this. Okay. This means if the temperature is high, for example, in this case, if the temperature of the substance is high, its entropy change will be low. Okay? So when we load these two relationships, we can write the change in entropy of a system is like this. We can use it like this. So what this means? This means when the system gets heat from the environment, okay, and the heat is here. The more heat, the more change of the entropy. And then divided by temperature. Temperature is the temperature of the system. So if the system at high temperature, and this number will small. Okay. So here we can see how to calculate the entropy change of the system when it gets heat from environment. Okay. Okay, now we can use this equation to calculate the entropy change at the transition point. So at the transition point, the temperature remains constant. What does this mean? Transition point, what is transition point? Transition point means like the ice changing to water, zero ice changing to zero water. Okay, so when the ice changes to water, we know we get the heat, right? We need to get the heat, and do you remember the curve of the temperature? So at the melting point, the temperature of the ice will not change, right? Because it gets heat. The heat used to melt the ice, so the temperature of the system will not change. So at the transition point, the temperature remains constant. Since the transition takes place at a constant pressure, and the pressure is one atom, right? When the ice changes to water, we don't change its pressure, right? So enthalpy equal to the heat. Enthalpy also heat, right? The heat is when it changes the ice, we call it, and the heat is also called enthalpy. It's called using delta H. So do you remember delta H, right? So entropy of vaporization, this guy, equal to, we know equal to heat divided by temperature, right? So the heat is enthalpy, vaporization is enthalpy. So, and the temperature is the boiling point. It's boiling point, right? So we can use this equation to calculate the entropy change when like the vaporization is like water changes to gas, liquid water changes to gaseous water. Okay, and we know this number we can measure, we can get from environment, get from the experiment. So we can use this number to calculate the entropy change. Okay. And if fusion is like from water, liquid water, from ice to liquid water, and we will also be using is fusion enthalpy, calculate the entropy. Okay. Here there are two numbers. One is entropy, one is enthalpy, one is entropy. So we can use the enthalpy to calculate the entropy. Just using this equation. Okay. So if the liquid, solid, and gases are in their standard states, so what do you remember? What is standard states? What is standard states of substance? Standard states, it means the pressure. What's the pressure? If the pressure is 1 atm, okay, and the temperature is 25 degrees, so this state is called standard state. Okay, called standard state. So if the liquid, solid, and the gases are in their standard states, so we can use the standard enthalpy change. Okay. And of course, this is not standard, because the boiling point, the boiling point is 0 degree. It's not 25. This is just how to just tell you how to calculate the entropy change by enthalpy change. Okay, have a short break.